Good afternoon. Welcome to Science at Home. My name is Christine Okochi, and I am an outreach associate here at CIRES at CU Boulder, and I'm going to moderate today's session. So before I introduce our speaker, just a word about some logistics. At any time, if you would like to ask a question, feel free to type it in the Q&A, and when our presentation is over, we'll do our best to answer as many of those questions as we can. And so November, first Science at Home of November, our theme this month is polar science. And we have our speaker today, Dr. Ryan Cassotto, who studies glaciers. And Ryan has worked in the field in both Greenland and Alaska. And he uses some very cool tools and instruments like radar and remote sensing, which he's going to talk to us about today. So let's turn it over to Ryan.
Great, thank you so much. As Christine mentioned, I'm going to talk a little bit today about radar and remote sensing of glaciers. I think it's a good segue. I think next week there's an interesting talk as well on ice dynamics, and so I'll touch upon that, but this might be a good introduction to what's come about next week and probably the week after. So I'm going to just start with what a glacier actually is and sort of define that. So glaciers are big sort of frozen rivers of ice. They're reservoirs or rivers of ice. And so they generally start in high elevation areas, cold areas, and they tend to flow down and converge with other areas of glaciers and create bigger glaciers. And so shown here is an example, a cartoon showing where you might start up in the upper head wall of a glacier region in this high mountain area. Eventually it'll flow down and converge with these other glaciers to create a much bigger glacier, and in some cases like an ice field or an ice sheet. And so this is just myself showing some images from the Worthington Glacier in Alaska, near the head wall of Worthington, and then another image from the Juneau Ice Field up in Alaska as well, so more of a much lower elevation area. And so glaciers form essentially by the accumulation of snow, obviously. And so over time, over many years, snow accumulates. It doesn't melt in the summer, it keeps accumulating, and over many, many years, eventually starts to compress and compact. And when it does that, we have this sort of metamorphose, or this transition from a snow into glacier ice. And when ice gets big enough, or when the glacier ice gets big enough and thick enough, it starts to flow under its own weight, under the force of gravity. And eventually it'll start flowing. And so this next, I have a video on the next screen, which I'll show you in a moment, and it's showing a couple of things. And before we get started with the video, I just want to explain, this is actually the Tidewater Glacier at Columbia in Alaska. And what you're seeing here is the terminus where it flows into the ocean. And you can see these little cracks called crevasses. And as I play the video, you'll see that these are moving forward in time. So this is a 10-year time lapse. And I want to keep in mind that it sort of conveys that glaciers are always flowing. They're always flowing from higher elevations in the mountains down to the lower elevations. And in this one, it's a coastal region. And there's a bunch of other dynamic processes as well, such as iceberg calving, which is the breaking off of ice. And that'll be talked about probably a little bit next week. But I'm going to go ahead and just play this time lapse, these 10 years of videos. And as it gets started, 10 years of snapshots. And as you start to see, the glacier is flowing. It's actually moving. Right, by definition, a glacier has to move. It can't just sit there and stagnate. We may not see it if it's out there for a few hours, but a glacier has to move over time. And so you can get a sense, there we go, that's now it's picking up. And so I'm having some video issues here, but mostly you can see that the glacier is starting to move. There was a scene back there where you could see that the crevasses were moving towards the ocean, right here, like there. So these are just really a good example of glaciers flowing from the upper regions here in the high mountain regions, flowing out towards the ocean and where it terminates there and creates icebergs into the bay. And so it just really conveys that glaciers are, by definition, moving at all times. So that's great. So why are glaciers important? Glaciers are important because they occupy about 10% of the world's land surface by area. But although it's only about 1/10 of the land surface, it actually occupies, or rather it locks up, about 69% of the world's all the fresh water. So if you think about all the reservoirs, the groundwater, lakes, streams, all those sort of things you might see walking around in the natural world, that's only 1/3 of what actually exists and which locks up in fresh water globally, and the rest is locked up in glaciers. And why it matters is that because it contains so much water, changes in the glaciers end up affecting sea level. So when you have more land ice, you have sea levels that go down globally, and when you have less glacier ice, you have sea levels that increase. So there's sort of this inverse relationship between how much land ice you have versus where the ocean levels are. And over geologic time, these things shift in both directions. Right now, we're going through a warming period where currently more snow and ice is being discharged, being melted and evacuated into the ocean that gets replaced each winter through snowfall. And so because of that, the ice sheets are getting smaller and sea levels are going up. So how do we know that? Well, we have to actually monitor that, which is no small task. If you think about the two major ice sheets that we have today, and those are Greenland, which is in the North Atlantic. This is a major ice sheet. It contains about 7 meters of about 20 feet or so, about the height of a house of equivalent sea level rise. If it were to remove all the ice and melt it and put it in the ocean, it would increase sea levels globally about the height of a single-story home.
Excuse me, Ryan, can I interrupt you for 1 second?
Sure.
We have some requests from people saying that the slides are small. Is it possible to go to presentation mode so people can see them full screen?
Oh, yes, of course.
Wonderful.
Is that better?
That looks great. Thank you.
Yes. So, as I was saying, so the major ice sheets, there's Greenland, and there's also Antarctica, right? And Antarctica is much, much bigger. It contains about 60 meters of sea level, so about 6 times, or rather 8 times as big as Greenland. And so these two areas, they're massive, they're rapidly changing and melting, and so monitoring is really important, but it can be quite difficult due to their extensive size, right? It's really hard to get there physically, and then once you're there, these are massive areas to cover and to get measurements from. So what we do is we use a tool called remote sensing. And so remote sensing, you may or may not have heard of it, but you may have heard of the electromagnetic spectrum. And the electromagnetic spectrum is essentially anytime you use anything electronic, if you're using a radio or using a cell phone or a microwave or a TV remote or any remote, these sort of things all use the electromagnetic spectrum, different wavelengths of electric energy that you use electronic instruments to measure, and it sends a signal. And whether you're radio or cell phone, it's all those waves are traveled by electromagnetic waves. And remote sensing is using these waves to acquire, to process, and interpret that data from ground, aircraft, or space-based instruments using different wavelengths. And so you're actually using this data to sort of understand the processes that are happening at or just below the Earth's surface. And so as I mentioned, there are basically 3 different types of remote sensing platforms that exist today. And those are basically airborne. These can be drones or airplanes or helicopters. You could have ground-based instruments as shown in the lower left. And this is an imaging radar system at a glacier in West Greenland. And then of course we have the satellite-based systems. And each one of these has a certain advantage or disadvantage. For example, a ground-based system, you could sit there for a few weeks and get lots of data points over the course of a few weeks. But it's really hard to leave it out there for, say, a couple of years. Whereas satellite-based instruments, they're always monitoring. They're always monitoring at all times, except you're only able to image the same part of the Earth every so many days. And it could be every week or every 2 weeks, but you're only going to get images, or you're only going to get surface information every couple of weeks. So the best approach is sort of use some combination of all of these things to really understand the processes of Earth that are changing along the Earth's surface. And this is basically the foundation of remote sensing. And there are 2 primary sensor types, and what's called an active sensor and a passive sensor. And a passive sensor is much like your camera. You might take a photograph, you might be outside, and really what you're doing is measuring the light, right? So the sun is emanating light, you're taking a picture of your friend, and you're using the sun's radiation, the sun's light, to provide the energy source from what you're capturing with the camera. Passive sensors work very much in a similar way. And so sometimes they're taking basically optical or digital photographs from space. They may measure the surface temperature of things. These are sort of passive sensors. And so you're using the natural environment to understand what's going on. And the active sensors are where more radar sensors come in. And this is you're actually generating this radar wave, and then you're measuring how much gets back. Much like if you're a fan of baseball and you see when they use radar guns to measure the speed of a baseball or a tennis ball, or law enforcement if they're measuring a speeding vehicle. It's the same principle. You're basically measuring, you're sending out a signal, you're receiving it back, and you see how long it takes between those acquisitions, between those radar waves, to understand how much has changed and over what time. And just some examples of what we do in Greenland. So this is showing from a passive sensor. This is actually the same satellite. It's called a MODIS satellite, and it actually looks at things in the optical band, or like I said, a photographic picture, much like a camera, a really super duper camera. And it also looks at the thermal properties. So it's looking at surface temperatures. And in this figure on the right, if you see my mouse or not, but there is, this is in West Greenland, and you see the ocean here. You can see some cloud cover in this region here, and you can see what's called a fjord. These are like channels in the ocean that flow into the like bays, sort of. And you get the main part of the ice sheet that's here, along with some sea ice, and you can see it blown up in the lower right here. And so this is part of these fjords. This is ocean water. This is sea ice. And then as we go further up, you get the main part of the ice sheet here. The same image taken at the same time, looking at it from a surface temperature perspective. We can now tell the difference between the temperatures of the icebergs in the fjord, of the glacier ice sheet itself, and warm fjord waters and ocean waters out here in the ocean. The other thing you see is on the upper image here, because you have this cloud cover here, you could actually measure the surface temperature of the clouds. So the one thing about passive sensors, they're only measuring at the surface. You can't see through clouds. You can only measure what's going on at the surface. And so here you're seeing the difference in temperature from the cloud top, which is really cold, from the ocean, which is relatively warm, and then you can see the sea ice and icebergs in the fjord here. And these are some of the ways that we use remote sensing to measure basically surface temperature, to understand the temperature differences in these regions. If we have snow here, you can see what the snow temperature is, or if there's bedrock, if there was no snow, you can see what that temperature is. So that's just one example of using passive sensors for this type of, for glaciology. Another thing we do, is use it to monitor surface melt. And so this is the same, a very similar sensor, and we're looking at how these changes occur over time. And so in 1992, this is the Greenland ice sheet, and this pink area indicates regions that were the maximum melt extent. And so only the lower part of the ice sheet was melting. The areas near the coast were melting, but all the interior was not melting. By 2005, some 13 years later, the area of the ice sheet that was melting now is moving closer to the interior of the ice sheet. It's moving higher up in elevation. So we're showing more of the ice is now melting. And then in 2012, in July 8th, 2012, it looked a lot like it did in 2005. But just 4 days later, there was a very big extreme melt event. And every single area, all the ice in Greenland, or all the snow in Greenland, was melting on that one day. This is a really unusual period of time. And it sort of highlights the fact that all this is using satellite remote sensing. This could not be possible. You could certainly go up there and maybe spend a couple weeks gathering melt measurements, temperatures, and melt water, but you're probably going to get a dozen or so measurements, single measurements spaced throughout time. You're not going to get the same coverage, the same sort of data on an ice sheet wide scale as you would from these sort of passive sensors. Oops. Okay, so that was a quick introduction to passive sensors. The other sensor is an active sensor, and this is where radar comes in. So don't let these colors fool you. Basically, what it is you're imaging the ground and you're measuring the return at a later time. And what you do is you just map the sort of how much has changed over that time. And what this enables you to do is measure speeds, glacier speeds. And so that's sort of the basis of this. And what we do is using space-based radar, we could do this along the entire ice sheet. And so this is a movie generated by NASA and put out by NASA that shows speeds along the ice sheet. And so here, yellows and oranges indicate very slow or minimal flow, minimal speeds, whereas the purples and blues show areas with fast speeds. So this is actual glaciers flowing. As you remember the previous video showing the crevasses and the ice moving towards the ocean, this is now showing a depiction measured from satellite of all the glacier flowing, all the glacier ice in Greenland flowing toward the margins and into the ocean. And you can see these little arrows actually depicting the flow directions of the ice of Greenland. And again, before we had satellite remote sensing, this was not possible. You would go out there with maybe a stake, a compass, a GPS, and you could measure certain points. But until we started doing these things with imaging radars and understanding how the speeds vary, you weren't able to do that at an ice sheet wide scale. And this is something that remote sensing glaciologists like myself do. We try to understand how the speeds are changing over time in response to a lot of the current changes that are going on in our climate. And as it turns out, the warmer the ice gets, the more water it produces. And when you add more water to the system, it allows the glacier to flow faster. And so we're actually monitoring these changes to get a sense of what, how this looks on a sort of large scale system, the entire ice sheet in this circumstance. I'm going to skip over this slide. We've sort of talked about that enough. The other type of radar that we have is what's called an ice penetrating radar. And this is a way to actually look through the ice sheet to the bottom, to the bedrock beneath it, right? The rock surface is underneath the ice sheet. And so if you were to think about the Greenland ice sheet, like the pictures that I just showed you, and magically remove the ice and just put it in the ocean, then this is what the underbelly of the ice sheet looks like. And this region here, like in the upper right, this blue area indicates areas that are below sea level. And so what happens is the ice sheet is so thick, it actually pushes down on the Earth's crust and depresses it, right? And so where it's thinner along the margins, you see these mountainous regions. This type of data was not available 10, 15 years ago. And so this is newer technology that we're using to penetrate through the ice to understand how much ice thickness there is and how that evolves and changes over time. And I think I'll end the talk here in this little video, another video from NASA, that sort of talks about those processes, explains a lot about glaciology in general and about the ice penetrating radars and what they're used for.
For decades, scientists have been probing the Greenland ice sheet from the ground, air, and space. Now a new study uses those observations to see within the ice sheet.
Oops. Excuse me.
Laying bare a tale more than 100,000 years in the making. When we look inside an ice sheet, we can see distinct layers formed by thousands of years of snowfall. As snow accumulates, these layers get progressively compacted into ice, which then flows under its own weight. To get a precise history of a particular spot on an ice sheet, scientists drill into it and recover ice cores, which provide a record of the ice's age and what the past climate was like. Seasonal variations, along with ash from volcanic eruptions, show up in the cores, allowing us to date the ice and correlate samples from different sites. To extend this age information across the ice sheet, the best tool that we have is ice penetrating radar, mounted on aircraft flying low over the surface. Radar transmits electromagnetic pulses into the ice and records the reflected signals, allowing us to track the depth of the layers detected in the ice. Since 2009, NASA's Operation Icebridge has flown over Greenland more than 100 times with a wide variety of instruments, including radar, and produced vast quantities of data, adding to the work from many other missions. This has allowed researchers to generate a three-dimensional map depicting the age of the ice throughout the Greenland ice sheet. This 3D age map shows that three distinct periods of climate are evident within the ice sheet. The Holocene, shown here in green, the last ice age, shown in blue, and the Eemian, shown here in red. The top layers from the Holocene period formed during the last 11.7 thousand years and are fairly flat and uniform, though the thickness varies depending on how much snowfall occurred. Below this, Deeper within the ice sheet, we see layers that formed during the last ice age. Layers from this period are darker and more complex, having been further squeezed and sometimes folded as they flowed over the rugged bedrock below. Deeper still are layers of ice left over from the warm period before the last ice age, more than 115,000 years ago. Eemian ice can reveal how the ice sheet responded to a period of warmth similar to the one we are experiencing today. Several ice cores have recovered Eemian ice, but it is difficult to interpret. This new map of the age of the ice sheet shows that there is more Eemian ice than expected in northern Greenland, where it may be easier for scientists to collect and analyze. This new analysis reveals a 3D map of the age of the Greenland ice sheet, from the oldest Eemian ice to the layers deposited during the last ice age, to the ice that formed during the Holocene. The response of the ice sheet to past climate change led to its current age structure. Further study will help us better understand how the Greenland ice sheet will respond to today's changing climate.
Great. So, so I just summarized things and just to wrap up the talk. Just a reminder that glaciers and sea levels vary over geologic timescales. So these are like many thousands of years. And when you have more glacial ice on land, you have lower sea levels and vice versa. And currently glaciers store about 2/3 of all the fresh water on the planet. And human-caused climate change is affecting the natural variability of the glacial sea level rise cycle. And remote sensing, such as the examples I've shown you here, provides scientists a way to measure the speed, the thickness, the melt, and the glacial extent, so we can fully understand how these quantities, how they change over on different time scales and different spatial scales, and allows us to look at the entire ice sheet, which would otherwise be impossible. And so with that, I'll take any questions, and I just thank you for your time.
Well, thank you, Ryan. We are going to have about 8 minutes, I think, to take some questions. So if anyone out there in the live audience wants to type a question in the Q&A, we'll get to them as many as we can. And while people are typing, I have a question. So you mentioned that how things like remote sensing are changing sort of the scale that scientists can look at with these glaciers. But I'm wondering, like, in your work personally, what does it look like in a typical year, sort of how much field work you're doing versus how much you're doing working with data that's from things like remote sensing, and how do you see that changing?
Sure, yeah. So, I mean, one of the things that remote sensing allows us to do is obviously look at things at much grander scales, but you still need a way to validate that data. And so what happens is most times, usually people go into the field once or twice a year, and usually, depending on what your objective is, you might go in the middle of the summer if you're looking at peak melt. Or a lot of times what I do is I go like in the springtime before the melt begins, and at the end of the summer when the melt has finished. And so that it gives you an idea of where you can look at two different time periods, two different seasonal time periods, and understand the changes that are going on there. So it provides you ground truthing data to understand and validate what you're actually looking at from the satellite. Sometimes it's really hard to interpret what exactly you're seeing. And so being able to go there in the field, conduct field studies with ground truthing measurements actually gives you that sort of basis. And that's where a lot of those terrestrial measurements come in.
Awesome. I have one more quick question before we get to some other audience questions. What's the coolest thing you've seen while you're out there on the glaciers?
Yeah, so I've been fortunate. I've been on the ice sheet itself, in the center part of the ice sheet, and it can actually be a little bit boring. And I can only say that because a lot of the really exciting parts are on calving glaciers. And this is a picture showing Jakobshavn Isbrae, a calving glacier in West Greenland, one of the highest iceberg producing glaciers in Greenland. And to look at a calving event, which is the breaking up of icebergs, you really can't explain it. It's just a spectacular image. And just we usually camp out there for 2 or 3 weeks, and you could just hear the rumble. Usually hear it before you see it, and then you eventually you kind of pay attention when you see the whole thing unfolding. Is a really spectacular event, and I consider myself quite fortunate to be able to view some of that. And there are tourists that go there, and there's actually an image here of a helicopter that we have captured over the terminus of Jakobshavn, and just the full scale of what the helicopter looks like, and then actually just what it looks like from where our perspective, just to provide some scale and the size of the
Wow. That's pretty cool. Thanks. Because we're running out of time, I want to get to some questions from out in the live audience. So Iris Woodley has asked, is glacier ice colder than regular ice?
In general, yes. So it is. So it usually in the middle part of the ice sheet, as you dig down, the like just below the surface could be 20 to 30 degrees below zero. And so usually that's where the coldest part is, and actually gets warmer as you get closer to the base. And so it's really hard to find ice, like in your freezer, for example, that's going to get that cold. And so it absolutely is colder than say, man-made ice.
Great. We have another question. Is there a way that we can get the ice that's over 115 million years old?
115 million years?
Yes, that's our question.
No. So the oldest ice that we have is about 800,000 years. And so the last, and that's in Antarctica, where actually the accumulation rates are lower. So in Greenland, the record goes out to about 120,000 years. And that's where that last video was talking about the Eemian ice. And so we knew that it was there. There have been ice cores that were able to drill through the icing and retrieve some of that. But now that we have this ice penetrating radar, we actually have a better idea of where the ice is if we choose to go and dig some more or drill some more holes to do basically some geochemistry on the data, on the ice cores.
Great, thanks. I don't see any new questions coming in. Oh, when I skipped another question from Iris Woodley. Why are there glaciers?
Why are there glaciers?
Why are there glaciers? Yep.
Great question. So glaciers exist, and when you get enough snow accumulation and ice accumulation without very warm summers. So the ideal condition to create glaciers, believe it or not, or to generate glacier growth, is actually warm winters and cool summers, because those two conditions allow you to actually have more accumulation in the wintertime and less melt in the summer. And if you do that for long periods of time, you actually develop these glaciers. So you need cold temperatures, you need seasonal variations, and a lot of that boils back into sort of orbital conditions, the position of the Earth's globe relative to the sun, which varies over time. So on big grand scales, a lot of it is controlled by orbital parameters, and on smaller scales, it's controlled by atmospheric temperatures, climate, and those sort of things.
Thank you. Well, we have a couple more questions coming in that I want to make sure we get to. Let's see. What would happen if there were no glaciers?
What would happen if there were no glaciers? Well, for one, for example, they actually help control some of the weather patterns, right? So having an ice sheet in the middle of the North Atlantic actually controls the jet stream. And so it actually factors into the temperatures that Europe experiences, the air temperatures, for example. There's other oceanographic conditions as well, right? And so that actually ends up cooling some of the ocean, which factors into some of the oceanography. So you basically have these heat that gets transported throughout the globe in the ocean, and having these cold glacier ice masses at the poles actually affects how much heat gets distributed and how it gets distributed. That's on the sort of continental scale. And then on a local scale, a lot of communities rely on them for freshwater resources, right? Like in Europe, for example. And so these are actually they're freshwater reservoirs. And as they melt seasonally, they provide significant drinking water and irrigation water for these communities. So without glaciers, that would actually, none of those things would exist.
Great, thanks. I'm going to see if we can squeeze in a couple more questions. So someone has asked, what is the average precipitation in Greenland, where you have studied glaciers?
Yep, so it averages on snow, usually anywhere from 3 to, I would say an average about 3 meters a year. So about 10 feet of snow a year, but it gets more than that. It can get up to 5 or 6 meters a year. And that's usually what you're going to get. It varies along the ice sheet, but those are the sort of typical ranges that you might expect over the ice sheet.
Cool.
Was there a second part of that question?
Nope, but there are definitely some more questions. So let's see if we can squeeze in maybe one or two more. How long was the warm period between the current ice sheet to the Eemian ice layer that you had mentioned?
Yeah, so we know the Eemian was about 125,000 years ago. And we were able to tap into that section of the ice. And then there was a glacial period where that was like the 125,000 years to about 20 or 10,000, 12,000 years. And that was the most recent glaciologic or glaciated period. And then the current period is where it's been more of a deglaciation. And so that's the more Holocene. So the length of period is probably in the Eemian I think it was on the order of 100,000 years. I'd have to, yeah, that's about an estimate.
Great. Let's see if we can squeeze in one more. We're at 1:30, but this is, I think, a great question to end on. Someone has asked, Parker has asked, what can I do to help the glaciers?
Yeah, so I mean, the best thing that you can do is try to reduce your carbon footprint, right? So whatever that looks like, if you're doing more recycling, if you're using more carbon neutral vehicles, taking more public transportation, those sort of things actually reduce our reliance on fossil fuels, which are the biggest contributors to increased carbon and increased climate change right now, climate warming. And so those are just some simple things that you could do to help reduce that. Even as things like at home, turning off lights and electronics when you're not using them, those sort of things are another thing that you can do to help fight that.
Well, thank you so much, Ryan. This has been great. Thanks for sharing your work. And thank you to everyone who tuned in live and asked questions. I apologize if we didn't get to all of your questions, but you can watch the recording of Ryan's presentation on the Science at Home website and tune in for future Science at Home webinars.
Great.
So thanks to all.